Many thanks, Peter, for the invite also, and for the kind introduction. And it's super cool to be here. I follow for a while already what you do. I think it's great, and especially great to see like on the chat, so many people from around the world actually. So I'm very, very excited to speak today. And please, as said already, interrupt me anytime. Let's make this interactive, and let's dive in into one of the fundamentals actually from 2D and 3D computer vision. So I guess you can see my video. So depth sensing is actually quite important for all sorts of augmented reality. For instance, if you want to perform something like this, where you augment a video stream live, you really need to know how far away the person is. In that case, my head. And not only that, you also need a bit of information about the pose to make this most realistic, to make the picture big if I'm close, and especially smaller if I'm far away. So in the lab at Technical University of Munich, we focus around these augmented reality applications for mobile, but also for other sensing devices. But not only this, 3D computer vision is also essential for applications such as robotics, where, for instance, the general bin picking, pick and place procedure would be a requirement where you need to know how far away objects, how far away walls, how far away a human is from the robot. And given that I currently work at the Chair for Computer-Aided Medical Procedures, we make these things also be applied in the medical domain, where it's also necessary that they are redundant, they work safely in an environment where both patient and surgeon is involved. So many of the works I'm glad to present today are actually within the framework of our collaboration. So I am very, very glad that I work at the interface between research in industry and academia, having been in industry for quite a while and now in academia for 2 years. So I had the pleasure to work with great people from multiple universities around the globe, but also from leading research institutes in the industry sector. Especially nowadays, the interface is not so separated anymore. So universities and industry work very, very closely together. And I've seen already in the chat that we have like both here from like young professionals and professionals, but also for people from university. So to give us a little bit of an intro of what we do in the lab and then what this talk will be about, let me give you a little bit of an overview. So in the lab at the Chair for Computer-Aided Medical Procedures, we focus on the computer vision, which is the technology necessary for many of the medical applications we do. And we start really close to the sensor. Sensor meaning a 2D or 3D sensor that gives us information about our surrounding. So that could be, for instance, an RGB image, such as we see here on the left, and the distance measurements from this. And then on top of this, such as we have seen in the beginning, you can build augmented reality applications. You can build all sorts of interactions for robotics that directly follow the image, the processed image and neural networks working on those. But you can also more abstractly work on scene graphs that abstract the data coming from sensors or individual sensors to quite an high abstraction level. For instance, in that case, where you have 3D information of a room and you abstract it to the level of chairs, floor, and the interaction and also the geometric interconnection between them. Today, we really focus on the 2D, 3D case of this very close to the sensor, and answer the question through a stroll through the literature on how we can actually get 3D information out of our 2D sensors. And this is not a trivial task, because most of the time we measure through projection. And that being said, typically we have a 2D grid, a pixel grid, like we have here on shown on the left. And this 2D pixel grid is actually a projection of the real world. And the way going from this projection into the 3D information is an ill-posed problem. So there are infinitely many solutions of a 3D object that projects into a 2D image. And just from looking at a 2D image, you cannot resolve that easily. It's just as such as illustrated from this image, for instance. Let's motivate this also from a perception perspective. Like we as humans perceive the world in 3D, and we do so by actually using two eyes. So we perceive the world from a left and from a right eye. And by doing that simultaneously, we are able to predict how far away an object is from us. So in a case of like a binocular observation with the left and the right eye, we have a specific distance between these eyes and are then able to triangulate and also focus on objects within the world. So if we just see that from one eye, an object in focus or in attention might lie on this ray, but the second eye then sort of nails this down to a specific distance away from the camera. So if you look at this right image, for instance, by looking at the image, we are not able to determine whether what is inside this head is actually a dwarf or whether it's a person in the background. What helps us, though, to uncover what is the reality is experience. And experience that we know there are no dwarfs in our world, but this is something we can learn. And we will see in this talk how we can actually learn from data to determine the distance measurements for such a monocular view. But let's start from a perspective of what kind of data we typically have. So in a case where we have a camera or a smartphone or whatever, we can have a different kinds of data. In the most basic case, this would be an RGB image or a grayscale image. But if we have a second sensor, such as in the case of the eyes, we would have a second image which is rigidly connected to the first. So we can observe from a left and a right view. Other sensing devices, instead of passively sensing the environment, would actively sense. And a typical sensor, for instance, in autonomous driving and the automotive industry would be LIDAR. This is a sensor that senses actively distance measurements and can be combined with passive vision. We will see later how such fusion can be done, coming from a sparse set of LIDAR data together with a left image, for instance, to fuse for a dense depth map. So what does depth map mean? Depth map means the coding within an image of the distance. In that case, it's color coded. That means closer pixels in this image are more reddish, while further away pixels are color coded here in darker colors, in more bluish colors. And such an image could be, or such a depth measurement could be extracted from either a monocular view by learning it, and we will see how to do so, or also by looking at the scene from different perspectives. There are quite a lot of data sets actually that allow us to train this on pixel perfect data. For instance, here is one of the example data sets where we can, from synthetic data, create pixel perfect so-called disparity maps. That's like inverse depth, but also the RGB that comes with it. So if we want to try out our pipelines, we have perfect data on synthetic level where we can try them out before actually applying them to reality. But of course, we don't want to stop with synthetic data. We typically sense with real sensors, and there's a whole bunch of real sensors, and we will cover some of those modalities within that talk. So you see here, for instance, very popular sensors, such as the Kinect 2 sensor, which is a time of flight sensor, here is an RGB-D sensor with structured light and another RGB-D camera. So the topics we will cover today, and also probably the most popular 3D sensor modalities, they encapsulate a couple of passive and also active approaches. We will look into time of flight today, where an active shoot of light gets bounced back from the real world, and we measure the travel time of the light ray. We will also look into stereo vision, where we have a left and the right camera, as in the initial example of our eyes, together with an additional projector, which adds a little bit of structure into the world when we have no structure, for instance, by just looking at a white wall. This will help us then still to recover depth. But we will also look into other sensing modalities. For instance, the LIDAR sensor here, which extracts point cloud data around its sensing environment that can give us a sparse measurements that can be projected on the RGB image here, but also less costly data, which are currently also available in many cars, which namely is radar. You can see here, this sensor is much sparser actually than the LiDAR, but also less costly and currently already available in modern cars. But we will also look, while all these sensors are somewhat active, we will also look into passive acquisition. And passive means, for instance, we have a RGB image or RGB image sequence, and just from looking at the RGB image and by experience, namely learn to extract depth data. This is typically referred to as monodepth. And in case that we have not only one camera, but multiple, we can look at the scene from multiple views. That can be in this binocular stereo case, 2 cameras, but can be also many more. This is typically named multi-view stereo. To begin with, we start with time of flight. Time of flight is this active sensor modality where you have an illuminator. This illuminator sets a light into the scene, and we basically measure how long the light takes to travel into the scene and back. And by basically measuring the time, we can recover the distance, because for the time, the speed of the light is constant with c, and then we can measure its distance. How that actually works, because we cannot measure like slice by slice, how this actually works is that we have an illuminator that fires at a specific frequency, typically a rect pulse-like signal. So that would be something like this. While time goes by, we have here an active illumination. Then we have a time where there is no illumination, and then again, active illumination in a specific frequency. And while this illuminator illuminates the scene, we wait with the receiver camera for the light coming back. And the light coming back is then compared to this initial pulse and correlated. That means while we have during an active pulse, we have a light coming back, we basically measure the amount of photons popping in and also the amount of photons popping in when there is no light sent at that time. And by doing so, we can retrieve the distance by knowing the speed of light, which is constant, and retrieving the amount of time which has been taken until the received light comes. This would be delta t, for instance, in that case. And we need to divide by 2 because the light travels the way into the scene and back. Another way to perceive depth is actually active stereo vision. In that case, we would have a camera being passively monitoring the scene. And the scene could be something like we have here on the right, like this cube. The problem with this cube is it doesn't have any structure. So it's quite quite difficult to say if we, for instance, measure here a purple pixel, which part of the purple pixel it is. But if we have knowledge of the relationship to a projector, we can project a pattern into the scene or also repeat a pattern continuously. And by knowing the distance, we can then retrieve by knowing the distance between those and the rotation, we can then retrieve the depth map. The more tricky case, especially when it comes to low structure, would be we have two typically equal cameras for which we know a spatial relationship, and then observe the scene synchronously from two views, and then try to recover with these two views the distance. And that's where we start. So we will start a little bit with the background and the foundation of binocular stereo vision, look into how we can characterize this, and then continuously go to very recent literature and how it deals with this issue and maybe overcome some of the drawbacks coming up from such a setup. And why is this relevant? Well, now everybody has basically in the pocket one of those very powerful sensing devices. Well, this might be a bit of a saturation, but many of the sensors in our smartphones have nowadays at least two sensors, like two cameras on the back, maybe a camera on the front. Some have even a time of flight or LIDAR. And with this, we can sense depth. Let's start with an example case from two views. The geometry that is typically encoded from two views falls under the term epipolar geometry. Why epipolar geometry? Because if we have two views and we use the typical pinhole model, we can encode a so-called epipolar plane from a specific pixel that is coming from connecting the two pinholes with a specific pixel, let's call it XL in this case. And this plane determines part of this geometry. So for one such pixel XL, the world point, let's call it XW, could arise from any distance on this ray. So this could be close, could be further away. We don't know from just one view. But what we can do actually by looking at the second camera, namely here, this right view, which sees the same object, we can then determine and triangulate this point. And the reason why this is called epipolar geometry, where the epipoles are given by EL and ER here, is that all potential points arising from a pixel do lie on this epipolar plane, and they do project not into an arbitrary position into our other view, but actually all of them, they do lie on what is called the epipolar line on this other view. And the reason why this is interesting is when we want to get a distance measurement for a specific pixel, we don't have to look for this specific pixel on any pixel in the other image, but we can restrict our search space quite to a one-dimensional line, or at least, or even a line that is actually restricted by the image boundaries. And the trick here is determining which point is actually corresponding to one another. And that can be done by matching the content of the image. To get there, there are a couple of tricks to make the search a bit easier. And also they are the foundation of typical data sets you will find in research literature, which most of the time do not come in a setup which is arbitrary images from two views, but they have been pre-processed. And this pre-processing is called rectification. So let's suppose we have an object in 3D, and this object lives in the world. And two views from this object, which are rigidly connected, they might look like this one here on the left and the one here on the right. Now, in order to find a corresponding pixel from one query on the left image in the right image, we have seen that this boils down to a line. But what we want to do is now, we want to virtually map these two views onto a common plane, such that our search for the corresponding point, given a query pixel in the left image within the right image, boils down to a similar to just a search on one horizontal axis. That basically means that when we query and look for a point in the other image, we don't need to look through the entire image somewhere here, but we can just take the same y coordinate and look along this line. This makes the search space much smaller, makes the whole thing more efficient, and eventually enables also real-time applications for stereo-based depth estimation. And this is the foundation of many of the sensors we actually see. Typically, many labs work with the inter-real sun sensor, for instance, and the foundation behind the depth maps they generate is exactly this, this principle. So the question is, how do we warp these images onto a common line? So how do we virtually change the images that might be just in a specific rotation with respect to each other and on the specific distance? How do we make them aligned such that this epipolar line is now horizontally aligned and also aligned in the same coordinate? So let's look at this from a perspective of a schema. So we would start with something like this here on the left, where we have arbitrary images, which are rigidly connected with each other, but which are neither coplanar nor parallel. So an epipolar line in one image might just look like this, and all of them, they come together in the epipole. And in the other image, it might look just like this. So the process of rectification is now aiming to make these epipolar lines parallel and also make it possible that they have the same distance. So the first step would be to virtually map, and this is a homography, to virtually map these two images in a way such that they are parallel. And by doing so, we make the epipolar lines horizontally aligned, but they are not yet at the same distance. If we afterwards, and this process can then be also going from the very left to the very right, if we afterwards make them coplanar, then all of a sudden, if we want to query one point here with respect to its right image, we just are able to extend the epipolar line such that its partner needs just to be searched within this frame. And then once we have found the partner, we can then triangulate the point in 3D. That means, naively speaking, we could go pixel by pixel in the left image, look for its partner in the right image, and then do the triangulation. Of course, this is not very efficient, and there are methods that make this process a bit more efficient. We will look into that in a moment. So what does that mean in terms of distances? And I promise there won't be a lot of math in my talk, but very schematically, I think, because it's an underlying concept which will be necessary, let's look at this as the schema from the top. Let's say we have the scene where these are the original images, and they are rectified such that they are coplanar. And now we look at this scene from top. So this would be our left image. This would be our right image. And let's try to understand what it means now to have depth. And for this, let's look into this schema. And we see that Z, for instance, is in a proportion to B. Also, let's write this down by the intersection theorem. Z is in proportion to B in the same proportion as Z plus F. That would be this. Z plus F is in proportion with, with this entire thing. And that would be B plus D, let's call it D. So D would be the sum of dl and dr. And now if we calculate this for Z, we can, for instance, here multiply. Let's do this once. It would be ZB plus ZD equals ZB plus FB. So we can get rid of this and then solve this for Z. That would mean, Z equals FB divided by D. So it's actually a relative simple equation here that solves us for the distance away from the camera, which has only 3 parameters. And F, that is the focal length of our camera. So the distance between pinhole and our sensor plane. B is the baseline. So basically the distance between one pinhole and the other. So both of them, they are actually fixed parameters once we have a sensor set up rigidly mounted with each other. And the only parameter that actually changes is this parameter D. And D is called the disparity. So it's the difference in Y or X coordinate between one image and the other. And this is reciprocally connected with Z. So the smaller the D, the larger the distance, and the larger the disparity, the smaller the distance. So that can be understood from when you look into a camera from 2 eyes and you observe your finger. So the disparity would be very, very close, very, very big. And the moment that the point moves away, so in that, let's say in this image in that direction, your disparity becomes smaller and smaller. While at infinity, you are basically on the same point. What does that mean now for 2 images? Let's suppose you have these 2 images, left and the right image. You can see that those are a little bit from different perspectives. If you look closely, you can see the differences. And if you do that now for each and every pixel, you calculate the disparity. You can retrieve a disparity image which encodes in every pixel the distance, just by looking across the different epipolar lines. And retrieving this can be a little bit tricky. So we can do that pixel by pixel, which I said is not very efficient. And we can also do that robustly. And most of the modern methods, they do perform some learning. But the learning really follows traditional approaches. And the next part of the presentation will basically look into how these traditional approaches can be mapped into a learning setup, where really the same principle as we've seen in this toy example can be coped with on the entirety of images. So let's talk about how we can learn stereo vision. For this, we look into the classical problem. So the classical problem of stereo is basically you want to match left and right images. And for this, you compute a so-called cost volume that encodes this disparity differences. So that means for each and every pixel, let's say this is a pixel with X and Y coordinate, you look along the epipolar line and that would be here the Z direction, for all its potential partners in the other image, and you save a cost, and the cost would be the cost for matching. So if we do that in this rectified pair here, for instance, you have this pixel, and then you look in the corresponding epipolar line for all possible partners across this epipolar line. So that would be here for disparity 1, 2, 3, and so forth. Look in that cost volume for its corresponding partner, and the cost could be defined some cost that compares a patch in one image with a patch in the other image. And the more similar the patches, the lower your cost. And what you are interested in is to minimize this cost such that it represents best your disparity image. And in a learning framework, you would basically have a feature extractor that extracts features for each and every one of those pixels, or typically on a low resolution version of your image. For the left and for the right, which is shared because you want to extract the same features, and then correlate these features, and wherever they match most closely, you want to have a low cost, and you will have a high cost where they don't match so well. And then you basically look along these disparity dimension and optimize for the minimum disparity value such that you can get typically a low resolution disparity map out. And a typical learning framework then, because this step is quite costly, a typical learning framework then does some upsampling and retrieves the disparity map at a higher resolution. For instance, this can be done by linear upsampling, which is a differentiable operation, but it can also be done with the help of the RGB image here for this upsampling step. So how does this such a cost volume look like? Let's look through such a cost volume. So here is a typical image which people use to work with because there's a big data set. It's called Kitty. Kitty has this left and right images of driving scenes. And here you see just the left image for visualization such that we can compare this a bit better. And in the middle, you see a swipe through the cost volume. So that basically means we are now going through the cost volume, starting with a disparity of 0, and then increasing the disparity with higher pixel amounts. So basically looking through the cost volume for potential matches of the left image to the right image. And what you see here is a dark line, which shows us low cost that comes from far away, gradually closer to the camera. That indicates that in our disparity volume, or in our cost volume, there's actually in the cost stored the distance away from the camera. However, you also see that this is not a very strict line because it's a real image. So there is, in a learning setup, there's typically a post-processing step afterwards that makes this initial cost volume a little bit better for its disparity output. It's also higher resolution disparity, typically with some post-processing step. So this is actually this is actually taken from Sponta Lacoon. Sponta, I think, Lacoon. One of the very early, or actually the first learning framework that looked into stereo vision. I can provide the link later. You can see. So how do people took it from there? So now that we can learn this, let's look into other learning frameworks that people dived in. Here's a learning framework where self-supervision was explored with this camera. This is a RealSense D435, which has actually the possibility to activate and deactivate a pattern projector. So this is this guy. So we have a left camera, we have a left camera here. Typically, we do it inverse because we look from the camera perspective, a left and a right camera. And this left and the right camera do extract a grayscale. The sensor has also an RGB sensor, which is quite helpful to understand the scene a bit better. So that is also attached in this image on the top right. If we look at this without this projector, we would get an image such as the one on the left here. And we see there are parts of the image, for instance here, there's not a lot of structure. And if we don't have a lot of structure, it's quite difficult to actually perform this matching task. And you can see in the extracted image here that in these areas, our depth estimates are actually not so good. While if you have more structure, like on this pillow or on the sofa, the depth estimates, they become better. So the trick, what the sensor does, and this is what many structured light RGB-D sensors do, they send for a pattern out, which is for the human eye not visible. So you see this dot pattern on here. And this dot pattern just creates structure where there's no structure in the texture. So all of a sudden we have actually a structure on the background, and this helps actually to retrieve this distance measurements and to resolve the matching problem within the disparity map. And as an outcome, your distance measurement becomes significantly better. So I just see that that my quotations are somewhat disappeared on the. If you look online, you will find the slides, including the quotations and the citations. So here we see a framework which basically does use the help of RGB. So I said initially that because of the efficiency and also typically memory constraints, it's much easier to do this task of disparity estimation or distance estimation on very low resolution. For instance, here we have a low resolution rough estimate, which is here in comparison to the original RGB, significantly lower. But if you can use the help of the RGB image, then upsampling this from a very low resolution to a high resolution with the help of RGB can actually be quite significantly well done. In this very particular case, the authors, they proposed to look at this problem from the other side. So basically start from here and make sure that whatever they learn is an image-to-image translation problem, which does fulfill this constraint of having this low resolution disparity map here. Well, not everybody has a RGB camera with two sensors. So we will not always have stereo. And very recently, especially throughout the last 3-4 years, the research in depth literature has focused on the task, which is very ill-constrained, to generate distance or disparity measurements from just a single RGB image. Here, for instance, you can see this for a recent paper which Google published. So as I said initially, the task is very inconstrained for the simple reason as when we start with an image, we have an infinite amount of possibilities how our 3D world looks like. And these ambiguities make the problem very difficult to learn. The first methods that looked into that problem, they all work schematically very similar. So they start with an RGB image, they learn some autoencoder, and then decode a depth map. So you can do that with full supervision. So if you have the ground truth here, you can do that, but ground truth generation is sometimes a bit tedious. We will see in a bit also that even most modern methods, they somehow fail to generalize if the ground truth quality is not good. So that's why more recent methods, they basically neglected the fact of having ground truth here and looked into ways how they can use the data itself to supervise the process of learning here, which is basically called self-supervision. And for self-supervision, they explored essentially the same principles as people explored in classical literature, where they used a second camera or they used time, as we will see in a bit. But let's start with the supervised cases, and let's do it chronologically, how this appeared in the literature. Yeah, I'm very sorry that the citations are missing here. Please look for the shared PDF. So the first paper in that regard that learned from monocular depth to estimate distances started with also an autoencoder, but this autoencoder had one issue which was overcome later. And basically it had two fully connected layers at the bottleneck, which make it a little hard to be capable of inputting arbitrary aspect ratios and also arbitrary dimensions of images. But nevertheless, it was the first possibility where you input an RGB image and get out first a coarse depth map, so same principle as before, which is gradually refined afterwards using a convolutional neural network. So Laina et al. At 3DV, they did improve upon this with a fully convolutional residual network. And the good thing about the convolution operator, also again, let's spare the details, but it's essentially an autoencoder. The good part about doing this fully convolutionally is that you then can have arbitrary input sizes, because you don't have a fully convolutional layer in the middle that is depending on the size of your image. Ever since, in the supervised fashion, there have been a lot of progress. There has been a lot of progress. For instance, MIDAS and also this CVPR work from 2022 have quite increased the performance in terms of supervised methods a lot. So you see that, for instance, for a very detailed structured image with just one input, so no stereo here, MIDAS, which is trained on a set of a very big set of high quality ground truth, is capable in retrieving a decent depth map. This more recent work here, maybe I quickly stop sharing and bring up the slides which have the citations. Maybe that's a bit better. Give me just 1 minute, then you can sort of note that down. Might be a bit better.
Sure. In the meantime, we have a lot of people for this event today. I can say very informative and clear explanation, Ben. It's very easy to follow. Not the most easy of topics. boosting monocular depth estimation to high resolution. This is the paper from CVPR 2021. This is a good time for me to mention people in attendance. Again, anybody who can turn your videos, please do so we can see you. And if you have any questions or comments or anything that you want to talk about, feel free to use your own audio. It's the best option. If you prefer writing in the chat in Zoom, I'm following everything there so I could see it.
Great. Yeah, sorry I think I just included the slide numbers just before the meeting, and I think this messed up with my footer here. So now we have the citations, but we don't have slide numbers. It should be fine. So let's continue. So in the supervised fashion, we have gone quite a long way ever since. And we are now talking about very recent work. So this is CVPR from last year, which used also some form of test time refinement. So there's actually a process after learning that looks into optimizing this image, looking into structural things such that we can get very high detailed depth estimates for just a monocular input, which I think is amazing because imagine all the possibilities you have even using web images which don't have any depth sensing. Well, but this all has the downside of requiring a lot of supervision. Especially MIDAS has a very big data set requirement in order to train this. While undoubtedly being super beneficial for the field, others have looked into overcoming the necessity for ground truth data. And the way this is done in the literature is actually quite similar for the method. So the first one that looked into this were actually Garg et al. And also Shi et al. At ECCV 2016, where they started with a left image again, and they were after getting the depth for the left image, and then had again an autoencoder and estimated distance on the right image, which they then could sample with pixels from the left and then compare to an actual right image, such they can formulate a loss between left and right image. Unfortunately, the first trials to do so, they used an image formation, a module, especially the sampler here, which was non-differentiable. And while they could show first results, the quality was not as good as it could be. So a very, let's say, prominent and also very popular approach, which is referred to as monodepth typically, was coming from this group, Godard et al. At CVPR 2016, where they introduced a consistency check from left and right. So what they did is they input the left image into the autoencoder and then estimate left and right image, and they depth, and then they use the differentiable sampler to compare pixel by pixel between these two images. So they could warp a pixel along and again, we are coming back to the epipolar line, and with the help of the depth image or the disparity image to its corresponding partner in the right image. So if it would be this, that would be that. And then can formulate a loss on pixel intensities, but also on structural similarity between those. And you can do the same thing starting from right and looking for the partner in the left image. And this consistency check is something which is quite often done also in the stereo literature, but they did that for the first time also in monocular literature. And the cool thing about this is all of a sudden you don't need the ground truth distances anymore, but you can learn from having a pair of left and right images without ground truth. Well, while at first, as you see in the examples, the estimates are not perfect, you have to keep in mind those are learned without any ground truth. So what is the issue here? No, here still, let's say in a perfect world, we don't want this right image, right? You basically want a method that is capable of just acquiring with one camera and still has no need for ground truth supervision. Very pioneering, Su et al. In that CVPR 2017, they actually did exactly this. So they, instead of taking a right image, they took a sequence of images from one camera. Basically, a camera moving through the scene is used to supervise itself for the task of depth estimation. So how does it work? When you have a pixel, let's call it P, and you again want to aim for a network that estimates depth for each and every pixel. But you this time don't want to supervise this with ground truth, but you want to supervise it with its own temporal data. What they did is they looked at consecutive images before and after and learned aside of the depth network, they learned the pose network. And the pose network basically defines the pose, namely the warping from the rigid pose from position 1, where the first image was acquired, to position 2, where the second image is acquired, to position 3 and orientation 3, where the third image is acquired. If you have this additional information, then you can warp this pixel, knowing its depth value, onto the frame before and also onto the frame after. And then you can compare these pixels with each other just on the images. And of course, the pixel might slightly change, but you might find similar structures. So if you take a photometric and also a similarity metric there, you can then learn, even without a second image, to estimate distances. And again, we have gone quite a way ever since. Well, this was the first very pioneering work of Su et al. A very popular method nowadays is called MonoDev2. It's again from the same authors as we have seen before, Godard et al., and presented in 2019, which just learns which is capable of just learning from temporal data, but it can also learn from temporal data and stereo data at the same time to retrieve quite impressive depth estimates without the need of ground truth supervision. And the crux is this to make all the steps differentiable, and this warping especially differentiable, such that learning and backpropagation works best. Well, so yeah, now we have seen all these spatial cues going from right to left, and also a little bit of a spatial temporal cue going from image T to T-1 to T+1. Now we want to look even a little bit further into the time domain. And for this, let's look what we can do with it and why is it necessary. So if we have an image with the input, for instance, this cat, of course, cats are all over the net. So let's also do cats here. So we have this input image cue, and we want to do an augmented reality effect on that. And for this, it's not just necessary to get depth on one single image, but we want to make depth consistent across the video. And in order to do so, we don't want any flickering happening, such that our video effect is most realistic in the end. And in their SIGGRAPH paper, they really made this impressive video effect possible by a test time refinement. So they basically took all the images of a short video sequence in and then trained on the entire video to make it most consistent. But to have AR effects in reality, and especially ad hoc, such as I showed in the beginning, we want to have this available in real time. And in order to do so, consistency is not a very simple task to define. So when you look into literature, especially more recent literature, people are either focusing on accuracy, and they are getting very impressive results. But results, even for these very accurate methods, they tend to flicker. For instance, if you look at this part of the accurate many-depth network, which uses even at test time multiple images, the image and here the overlaid disparity map or depth estimate flickers a little. We do want to be consistent over time to have the possibility of having realistic augmented reality effects. So here's one of the networks Patrick Rukamp and others and from our lab proposed at 3DV last year, actually just last winter, which looks into not just accuracy, but also making sure that our estimates are temporally consistent. And I'll schematically go over this. Don't get scared from this big slide. Let's break it down and simplify it. So what we do have actually is exactly the same structure again. So we have an encoder and we have a decoder. Now we want to somewhat into this framework stick in a spatial and a temporal cue such that we reach this consistency. And the way we do it is we first aim for the spatial cue and then make it constrained on the temporal cue. And the way we reach this is with a very popular method nowadays, which is called attention. Let's look into this schematically, how it works. So we have a spatial attention for a specific pixel encoded by the features. I won't go into the details, but the details are in the paper, but I want to give you here the schematical idea about it. So if we have spatial attention, we can query a pixel and can look at its attention values across the entire image, for instance, a frame later or a frame before. If we do so, then we will get what is encoded here with the color coding. So this color coding is not a depth map, it's an attention map. And for this query pixel, you can see that the spatial encoding, looking for the correlating pixels with our spatial attention module, is basically looking mostly at these areas. And this works also for other images in the temporal stack. If we now do that naively in time, it is relatively ambiguous. So we have some attention here, we have some other attention here, we have some other attention here. So it somewhat gives us a result, but it's not very detailed. If we make this temporal attention guided by its geometric attention through a simple loss, which is essentially just looking into the difference between the minimum disparity difference between the depth here and its maximum value, then we can regularize this temporal attention with a geometric cue. So we first do basically this spatial attention, and then we guide the temporal attention with it. And what happens is that actually the temporal attention gets much more focused. And this helps later, if we have this spatial and temporal attention, to make our predictions later through time more consistent, while not losing the accuracy we don't want to lose, because I mean, there's no point in getting super accurate super consistency if we don't have accuracy. And eventually we end up with a method that is capable, if we use this input image, that is capable to overcome the consistency issues of very accurate recent methods. So many-depth, for instance, is a recent method just from last year. However, this method has these issues on inconsistent boundaries and also parts in the image, which appear especially if you change the viewpoint. So in order to to do these two images here, we changed the viewpoint of the camera with the depth map, which was estimated. And if you look at the comparison with LIDAR, you can actually see that the method we proposed at 3dV much more hits the LIDAR points which underlie here than from multiple views than the many depth method does. And what effect does it have? If you reconstruct the scene from 3 views, you can actually see that there are ghosting effects in the very accurate but temporally inconsistent many depth methods, while the method proposed by our group is temporally more consistent. If you want to check this out, feel free. The code is available on GitHub, so you can play around with it. And also in this paper, we introduced a metric that actually for the first time makes this consistency measurable without the need of using a tracker or some other consecutive bit, but actually looking just at some ground truth LIDAR measurements here, for instance. Okay, so now we have seen multiple views, we have seen single views, but we remained on RGB and on similar modalities. So we have also seen a bit of ToF. Now, actually 2 or more different modalities, they can actually benefit from one another. So if we have an active illuminator and we have a passive method, we can also join their cues and perform depth measurements that are even more powerful. But this has also some pitfalls. Let's look into a very realistic scenario at first, where we want to fuse sensing from 2 sensor modalities, namely time of flight and RGB. But we want to do it in a way such that it actually works in reality. So previous methods really focused on lab scenarios where you can see the time of flight data here, which has almost no noise, which is either due to the fact that they can power the device by current, or they have a high power device or very, very little ambient light. And then you get data which looks like this. However, time of flight sensing, especially when it's performed on mobile phones, has very big energy constraints. So you don't want to overpower your phone and run out of battery within seconds. That has the downside that you have actually quite a lot of noise on your data coming from ambient light and also from low power of your emitter. And you would still want to be able to detect distances in that area. And the way this is done here is actually helping the ToF image or the ToF input with RGB. However, this has a problem. And the problem is these 2 sensors, they don't look through the same pinhole. So typically you would have a sensor that is spatially related to the other. Let's say one of them is ToF and the other is RGB, but they don't look through the same pinhole. And the way this is aligned here can be a chicken and egg problem, because if you want to align pixels coming from that domain onto the other, you would need to spatially do that correctly. You would need the depth estimates already. And to estimate the depth is your task. So it's a bit of a chicken and egg problem. The way we did that here is actually by doing a very coarse alignment, just by unprojecting with the inverse camera and projecting onto the other image, and then refining later. So if you overlay this without prior alignment, it would look like this. If you follow this initial coarse alignment, so you can see here it's not very well aligned. If you do that roughly, you would get something like this. You can actually see in Y direction, it's already quite well aligned, but you see that these 2 sensors, they don't look through the same pinhole. So they have a little bit of a disparity offset. However, we use this coarse alignment as an input to make the task a little easier. So how does that work?
Sorry, one question. Like,
yeah, sure.
You back project the image without accounting for the translation.
Exactly. So
okay.
Here we don't have the depth estimates yet.
Mm-hmm.
So we just use the inverse camera matrix. If we had the depth estimate, our problem would already be solved.
Okay.
That's the chicken and egg problem.
Okay, I see. Thanks.
Yeah, thanks for the question. So this rough alignment is now done here in the on the RGB. So we align RGB to ToF, and then learn to encoders where we can fuse by concatenation, where we can fuse the low resolution feature, and then get out a first feature which is representing rough depth. And with this rough depth, we can do a spatially more correct alignment, which we do here from the top to the bottom to get best possible depth out. And here, for this alignment with the actual camera, that is what we have here. We have actually the translation. And the outcome, we are here again in a very high noise area. So the outcome is not perfect, but we can relatively compare to previous methods. So here, this is a typical office scene where you have strong ambient light by these lights on top. You have reflections from everywhere. And previous methods, they do show a lot of artifacts here in the background, and also on this couch scene, for instance, here, where you see not much crispiness, while our approach could resolve this with a little bit more crispiness, while also coping for the general scene structure in terms of depth. Okay, so this was real data with a lot of noise. And we have fused ToF and RGB. So now let's also think about some other problems where we can fuse data. And where the data might be presented in a different form. Let's start again with RGB, but this time have this typical automotive setup where our second modality is LIDAR. LIDAR is basically, as you've seen initially, is a sparse, but not as sparse as radar, point cloud measurements that can be on top that can be projected on top of the RGB image. And the task here, which is called typically depth completion, is the task of fusing the sparse signal to densify the full depth map based on the RGB. So while previous methods have actually this issue of training fully on ground truth data from the real domain, we, in this case, used synthetic data created from a synthetic rendering engine, and where we could create both RGB and LIDAR. So now that the problem we faced is if we use LIDAR just by sparsing it out, it didn't really work on real data afterwards. So the trick we used is we didn't want to touch ground truth from the real domain, but we used actually the mask that the LIDAR provides in order to sparsify our data on the synthetic domain. And you can see that when you use these masks, you can recover quite well even thin structures in the real domain while not actually touching any real ground truth. Because in reality, LIDAR data might not be always present. But it's basically, there are some renderers, and you can find the links also in the paper. There are some renderers which provide you the possibility to render everything synthetically, even with driving scenes. So let's go a little bit sparser now. So we have seen LIDAR, and we've seen ToF, we have seen LIDAR. Now let's go even sparser and then think about radar. So what can radar give us? Even a very sparse signal can actually help quite a lot. So, and here we tackle, with the help of RGB and radar, we tackle the problem of dynamic objects. So even most recent methods, let's recall MonoDev2, they can very nicely predict full depth maps. Dynamic objects are quite often problematic for the simple reason that when you use this monoDev loss where you project from one image to the other, stuff moves in between. And these dynamic objects then make predictions problematic and also the learning part. Therefore, monoDev estimates are often when an object comes close to you, are often undershooting these objects in terms of depth. And this becomes quite apparent if you change the view again. So here you see the view from a bit of a different perspective, warped with the depth estimate. So the actual car disappears in the ground. And this becomes quite crucial because in that direction, if you undershoot, you would assume your car is much closer to you and an autonomous application, for instance, would break. So you don't want to undershoot or also not overshoot on dynamic objects. And what we did here is using this very sparse signal to actually cure this effect. While it's not perfectly cured, you can see that using this slide data from radar can actually help to cure this problem in dynamic environments. And if you compare here, for instance, look at this image. So the colored points here are the radar signals. So it's very, very sparse. But it quite helps a lot, even compared to very recent methods. So for instance, here, this is again monoDev, which undershoots this image. Some other methods, for instance, Kasser et al. Here, do have holes where dynamic objects appear. And more recent methods that use also some kind of radar input, they are less crisp. Using our way, where radar is used both as input as a weak supervision signal during training, helps to actually cure this task and estimate correctly the distance of dynamic objects on the depth map. And this is especially interesting. So this project is in cooperation with BMW, for instance. This is especially interesting because radar sensors are built in already in many cars. So it's quite interesting to actually combine this modality with RGB. All right.
I have a question.
Sure, go ahead.
Going back to this radar thing, what is the trick or mechanism you use to translate the sparse LIDAR points into these dense depth maps? Like, how do you train it?
That's a very good question, actually. Mm-hmm. So as you can see here on this slide, So you can see here on the slide, the radar input is very, very sparse.
Yeah.
And just using the radar input as an additional cue will not bring us these results, as you probably suggested.
Actually, it's even sparser than I imagined. It's only one row of points, right?
Exactly, because the radar sensor senses in that direction. It senses mostly one row. Sometimes even looks underneath the cars because it's very close to the ground. The problem is twofold. So first fold, you look underneath the cars, and that creates measurements which are actually further than the one you are actually seeing on the RGB, because the RGB sensor is more up. So you need to filter them. You need to filter out the ones that are incorrect, and that's what we did. And the second problem is, and that's probably what you had in mind, the signal is so sparse, you need to somewhat artificially extend it. And the way we did is basically looking at the structure of the RGB image and extending the radar measurement guided by RGB to an area which is a bit further and a bit broader than just the single measurement. And that helped then to improve the measurements on the full RGB, and was a very weak, but was a signal that could overcome this dynamic issue.
Okay, so you feed the depth still over this extended area into the pixel related loss.
So exactly, you extend the measurement of your radar point into a bit of a bigger area, which can then be used as a loss, not just on the very pixel, but in a bit of a more extended area.
Exactly. Okay, thank you.
No worries. Okay, so we have seen different sensors. We have seen spatial cues. We have seen different sensing modalities such as ToF, radar, LIDAR. But as you've seen, many of the works cited, they are very, very recent. And in this area, there are a lot of open research problems. Let me give you my perspective on some of the very recent challenges, which might be the focus of literature over the next years. Many of the scenes are actually coming from autonomous driving. While these networks work quite well on areas which are outdoors, on scenes which show transportation, which show views from cars, indoors is still a big challenge. And not for all objects, but especially for some objects which are very, very inherent in our everyday life. And these might just be household objects like forks or glasses. Those objects, they provide big problems for depth sensors. And for the simple reason, because we have seen a time-of-flight sensor actually actively shoots light into the scene and waits until it bounces back. What happens if it hits an object which reflects? It reflects up on the object to a wall, back to the object and back to the sensor. And therefore, quite well overshoots its estimate for depth. Other objects, which are very often present in everyday life, just disappear on depth maps. Even though glasses are probably one of the most prominent objects in our household when you would think about a robot that should prepare your dinner table. And you can see that on many objects, even only partially reflective objects. And I think depth estimation on these type of problems will be very crucial to make these things happen in everyday life. And we started some investigation, and this is very, very recent, where we looked into learning pipelines that are trained on input, which is typically used in the literature. And we found some very interesting directions. So you would, for instance, for this scene here, you would hope that you find something like we show here in the middle, which is rendered. But what even a very prominent ToF sensor here, the RealSense L515, would measure is overshooting, are missing pixels, and objects that are completely gone from the depth estimates. What happens now if you actually train on this kind of data, which is called ground truth? What happens is that when you train with this is basically a monodepth pipeline, so it's essentially again an autoencoder on top of this image. What happens if you train with the ground truth here from the RealSense L515 is that you get very coarse estimates on the boundaries of objects. Here is the scene which has been seen during training, but from a different angle. So same scene, but unknown trajectory. And you see that even in this case, where it should somewhat at least have some clue about the objects, it does not infer very crisp boundaries. While if you train the very same network with more accurate data, your boundaries become a lot more crisp. You don't have this overshooting anymore, because the data is actually present in the RGB. And in that way, RGB can be a cue which has some benefits over a depth sensor, even if you want to estimate actually depth, because the depth sensor by nature of hardware is not capable of estimating the depth correctly. Okay, it might not be so surprising that training with better depth might give you better results. However, the improvement is very significant. It's 55% improvement in terms of RMSE here. And in vision literature, oftentimes sensors such as this are considered ground truth. So what does that mean for generalization? If you do train a depth estimator and show it a scene which it has not seen before, again, trained on real sense data, it fails horribly. Here, it's basically not capable of getting the distance estimates of this photometrically challenging object. The other object fully disappears. And even objects that are photometrically less challenging, such as these ones, they are not very well recovered. While simply a little better ground truth, here rendered again, with the very same network, quite well retrieves the distance of these semi-transparent objects. Even though a depth sensor would not be capable to see this, as we've seen initially, it would just look through. Actually learning on RGB data can help here quite a lot. And I think this is quite an exciting direction, because we see that counterintuitively, RGB data can provide a cue which is more powerful than using the depth sensor itself. And I think in the future, or I hope at least in the future, we will see more works that actually combine such ideas from RGB with actual depth sensor, because there won't be one modality that will solve all our 3D computer vision problems. There will be multiple modalities that are good at different problems and at different scenes and at different texture-rich or photometric complexity scenes, and combining them might eventually result in the best performance. With this slide outlook, I want to conclude, and I'm very, very happy to discuss further on this foundation of 2D, 3D computer vision, actually.
Wow, this is very elaborate and clear, actually, presentation, Ben. So thank you for that, first of all. People in attendance, good time for questions. There were a few remarks, I think also because everything was very clear towards the way, but still, if anybody wants to ask something, this is the time now. Otherwise, you'll only get the recording later. Go ahead.
I would like to ask something.
Sure.
Thank you for the presentation. It was very enlightening. I wanted to ask something that I think did not appear about speed of computation. If we want to do it on edge devices like on phones, what is the way to go?
So by experience, I have been working at Huawei. I know this problem quite well. So you have very big restrictions on computation, also to not overheat the battery. And there are things computer vision researchers typically don't think about. And I think there are multiple routes to follow. So one route, maybe going back to the principle of stereo, one route which is often taken is actually to minimize the bottleneck of computation to the very, very coarsest. And in that case, it would be whatever is most complex, try to do it on the lowest possible resolution where you still can get something out, and then try to help upsampling the depth to the level you want with some other cues. And typically, to make that on edge devices, you would have huge input. Could be on a phone, for instance, could be a 10 megapixel image. You can downscale it quite a lot, get a low resolution disparity map, and then using this image again to help here for the upsampling stage can speed up things. So there are many works that actually look into this. For stereo literature, for instance, there is a work from Camis et al. It's ECCV, I think 2018, that provides some information how the group from Google does that. The idea is basically you have a guided upsampling, which goes not one shot from low resolution to high resolution, but you go up a small bit in the hierarchy. So you go up to a medium-sized image, then you correct what you did wrong with the help of another modality, namely RGB, and then you go up even higher until you gradually reach the final resolution, and only correct the mistakes you did by upsampling. And the upsampling operator can be a quite trivial one, like a bilinear upsampling. And so you gradually go upsample a little, correct, and that makes things much faster. I think that's one trick. Mm-hmm. The other trick, of course, is to use time. So if you have, for instance, previous guesses, let's say you estimate from time t-1, you could use that as a prior and only again correct what pops into the next frame. I think those are probably the two most often used ideas.
Thank you. Thank you.
I have also one question. I'm mostly interested in this monodepth. And usually if it's completely unsupervised, you have your depth up to a similarity transform, right? So everything is up to a scale. So I love the work you've done with the radar, which solves this problem. And obviously you can also use LIDAR. Do you know what other methods are there where you can retrieve the real depth of an image?
Yeah, so you're absolutely right. Due to the projection, like the ill-constrained problem of this, you can retrieve only up to scale, because whatever you project onto the image can either come from a distance here or from a distance further and so forth. So there are a couple of different tricks to do that. As you already mentioned, using another modality, which is actually scale dependent, like radar or LIDAR could be one. You can, of course, take a second camera. So if your device on which you want to operate has a second camera, and those cameras are rigidly connected with each other, you can calibrate them and then retrieve automatically from the scale-aware calibration this information. There are some works that look into retrieving this data also from experience. For instance, if you couple this depth estimation with object detection or some semantic priors, where you know scales of stuff in your image, then you can retrieve it from there. For instance, if you know the average size of a car or the average height of a person, you can look in your images for persons or cars and gradually use and get the scale from this. Mm-hmm. But you can also couple with other non-image modalities. For instance, if you have a temporal cue, and especially in your mobile phone, for instance, you have also an IMU sensor which measures acceleration. You can couple this with your imaging pipeline and can then get the scale from the acceleration sensing.
Mm-hmm, mm-hmm. Okay. Yeah, thanks.
No worries.
Any others? So I think for now I'll start to close unless somebody has a question. Ben, very, very elaborate and thorough talk. really impressive stuff. Thank you for coming today and for sharing from your knowledge so clearly and interestingly. People in attendance, thanks for joining and for your remarks as well. Think we're gonna close now because I don't see any other questions. So again, this will be recorded and posted on YouTube. Anybody who wants to come back and re-listen something will be able to. There will be chapters so you can see it as well. This will all be published in the newsletter. Also, the link to the YouTube will be published in the meetup event. You'll have everything quite quickly. Ben, I wish you really, first of all, a good evening, good night now already for you and for me. And a lot of luck for the coming research. Looks like interesting stuff. You guys found a method that really seems to prove itself with the fusion work. So really interesting to see.
Yeah, many thanks for the invite. And also for others also on YouTube, if you have any questions, don't hesitate in reaching out. My email should be on this last slide. Let's bring it up once more. Don't hesitate in dropping an email so we can discuss with each other via email.
You know what? I'll even be a bit maybe rude and ask you and Patrick if you guys are on Discord and you're willing to join ours. Sometimes people have questions about what you do and other stuff. If you'll have the time to take it to answer, and to talk to people there, it'll help others as well there also. So please, you're welcome. I'm going to send out all the links where everybody can find everything. So whoever wants to join the Discord will be able to. I had it open and now it's not. There it is. Where is the Zoom? Oh my God, so many windows. I went lost. Okay. Yeah, now everything here is on the chat on Zoom. Again, thanks all. I will wish everybody a good day, good evening, good morning. And until the next time.
Thank you.
Bye.
For now.
Thank you.
Thank you.
Thanks
Bye-bye.
a lot. Bye.